So we have got the product in a quotient rule. So if your function is made up of two things, f of x times a g of x, then you can find its derivative y dashed by this formula. And if your function is made up of a fraction, f of x on the top, we'll call the bottom guy g of x, then you have this one. The top one is called the product rule. Product's the word for multiply. And the bottom one is called the quotient rule, and quotient could be thought of as dividing things. So let's just do some practice. Nice simple one. You just get the show on the road. This is similar to question 2. Right. Call this guy f, call this guy g. So you want to find his derivative. You write down the product rule. Because you write this rule so many times, I tend to miss out the f of x part, right? I just call it f dashed and that's good. You differentiate x to the 7 with the power rule. Multiply by the power, reduce it by 1. You then leave g alone. You then leave f alone. And then you differentiate e to the x, which is very nice because the derivative of e to the x is still e to the x. And then you have style points. And one is make it look like the original. And rule 2 is factor the heck out of it. So let's factor the heck out of this. What common factors can you get out of this expression?
E to the x.
Agreed. What else?
X to the 6.
And once you've done that, 7's left over, used up. So this is 7. One of the x's is left behind, the rest is used up. There's your answer. And that is considered the final form, right? The best looking version of the answer. Now, here's an example of a question where you really don't need to do the product rule, but it might be worthwhile to do it anyway. Couldn't I do this question just by foiling it out? You agree? I could foil it out and just do the power rule. But since I'm going to be doing the product rule and I want to get practice at it, I'll call this guy f and I'll call this piece g. So that means I can get a derivative f dash g plus f of g dashed. And if you differentiate this fella, you get 2x add 2, and you leave this guy alone, you get x cubed plus 7. And then you leave this guy alone, and then you differentiate that guy, and you get that. A lot of people just want to leave it that way because they think they've done enough, but we don't consider that good form. So we need to do some style points on that. This one, you have to do a little bit different from the other one. The other one, it was just pulling out some common factors. What do you think I'm going to have to do here to try and at least write it down in the way that it's expected to be written down? What do you think I should be doing?
Try to get common factors.
Well, you could, but not right now. What should we do with this before we start worrying about common factors, if there are any?
Yeah, multiply that out.
Yeah, so you're going to have to do a horrible FOIL. I'll do the quick version. 2x to the 4, add 14x, plus 2x cubed, add 14. And then you collect like terms. So that guy gets added to that, and then you have that fella. Next guy is x cubed, so that guy added to that gets me 8x cubed. I've got a plus 14x and a plus 14. And I'm pretty sure there isn't a common factor there, so we're finished. And this is considered the best format. If you look at what it was originally and you look at this, I hope you agree it's a little less complicated. Isn't it obvious now how many x to the 4s you've got and so on? If I look at this expression, isn't it quite difficult to know what various powers of x I've got when you do it this way? So you're actually simplifying it as far as we're concerned. Are we good? Any questions? Right. The best way to get good at product and quotient rule is to do as much practice as you can, right? You can never have too much practice, right? So let's add another complication to the problem. Definitely a product rule. All of this will be f. This little guy here is going to be g. It's going to be f dash g plus f of g dashed. Oh, that's a problem. So I'll do that on the side. Right, that's the guy I'm calling f of x. I need to be able to differentiate this guy, right? Because it has to go here. How do I rewrite this so that I can differentiate it? Because right now, x plus 7 square root of x isn't really cutting it for me. Rewrite this guy in a form.
Would it be 7x to the 1/2 or
It
x
would.
plus 7x for 1/2?
You're right. You nailed it. Guess you don't really need those brackets, but they're there. So now you can differentiate. You get 1. Power rule. Add 1 to the power and reduce the power by 1. Are we comfortable with that guy? Now, I could make that pretty, but, you know, I'm going to make the whole thing pretty. So I'm just going to leave it like that until the end and then, you know, do all the style points in one place. So f dashed is 1 plus 7/2 x to the negative 1/2 times g plus the untouched f, which I'm just going to write like that again, and differentiate him, you get e to the x. Okay, common factors. These guys are common factors. So I have a 1 plus 7/2 x to the negative 1/2 plus an x plus 7 square roots of x. There is not an awful lot more to do except rule number 1. Shouldn't it look like the original? Are any of those terms, do any of those terms need to be changed so that they look like the original? Who is it?
The 7/2 one should be 7/2x or square root of x.
Okay. There is no way in the world you would call that expression pretty. Would you agree? It's clunky, it's ugly, but you can't do more to it, right? There's nothing else you can do to make it happy, you know, make it pretty. So that's the answer, even if it's kind of unsatisfying, because don't you want answers to be nice and symmetric and tidy? And it kind of looks yucky when they don't work out that way. But there are going to be a lot of questions that are just as ugly as that one, right? And so don't worry about it when that happens. Okay, time to show you a quotient rule now. So a quotient rule is used when the original function is some kind of fraction. So this one is similar to question 6. There you go. And when that happens, the top is called f and the bottom is always going to be called g. And the derivative is this ugly guy. F dashed g, take away f of g dashed all over whatever g is squared. If you differentiate the top, e to the x, you get e to the x, and you leave the bottom untouched. Right, so that's this time. Take away. Leave that guy untouched, and differentiate the bottom. What is the derivative of 5 take away e to the x? Be careful. What's the derivative of 5 subtract e to the x?
So just negative e to the x.
You nailed it. Some people forget the negative. I guess it's because e to the x gives you e to the x, but doesn't 5 e to the x get you 5 e to the x, right? That constant term, in this case -1, is still there. Now, in this, I don't know, topsy-turvy world, we now have on the bottom that guy, right? Whatever g is squared. Now, what I'm going to do now is all style points. I am going to find out what this thing ends up looking like. And there are 2 totally different directions to go, and they both end up essentially equivalent to each other. Has anybody got any suggestions of what happens to the top row? What you might do to make it look pretty?
Well, I was curious, can you cancel out terms? Like the
It's-
5 minus e to the x? Or do you just combine like terms?
Well, you are allowed to cancel terms, but only if both pieces have a 5 minus e to the x in it. You're not allowed to cancel if one of them has it, but the other doesn't.
Mm-hmm.
It would be nice, because that would certainly make this simpler, but that's not going to happen in this particular case. May happen in the future. You might get one where both of them. Any other suggestions?
Well,
Nothing?
it looks like you could definitely cancel, well, you could expand first, but then you
Right,
could
let's
pull
expand.
out that e to the x.
So I like your thinking. Let's expand. E to the x times 5. Now be careful. What does e to the x times e to the x get you? I've already taken care of the negative. It doesn't get you e to the x squared. What does e to the x times e to the x actually get you?
e to the 2x.
E to the 2x. Now this one here I'm going to be extra careful about. Negative e to the x times negative e to the x. Would you agree that becomes positive? And isn't e to the x and the e to the x positive e to the 2x? Are you happy about that? Are you comfortable where distributing gave me these 2 terms and multiplying these 2 together gave me a positive e to the 2x? It's still over 5 minus e to the x squared. Can you see something really nice that's happened here? Agreed? Don't the e to the 2x's can kill each other off, essentially? So now you're left with and good news, we're finished. Would you agree that's as good as that can be? Now, you are not allowed to cancel this e to the x with that e to the x. If you were thinking that was doable, it's not allowed. And the reason it's not allowed is that this is 5 take away e to the x. It's not just e to the x on its own, right? So nothing else can be done. This is as good as it's going to get. Let's do another one. To that one. So the top's F, the bottom is G. The product rule is F dash G take away F of G dashed all over G squared. If you differentiate the top, you get 2x add 2. If you leave the bottom alone, you get that. take away. You leave the top alone, which is this guy, and you differentiate g dashed, and you get 6x plus 12. And then the whole thing has that guy on the bottom squared. So what I'm going to do now is FOIL these out, write them down, FOIL these out, write them down, and put a big minus in the middle, collect like terms and see what we get. So if you FOIL, you get 6x cubed plus 24x squared plus 6x squared plus 24x. That's those two multiplied. Take away. Has anybody ever done a 3 times a 2? It's like an expanded version of a FOIL. Right? I'll show you that on a separate piece of paper. X squared plus 2x plus 1 multiplied by 6x add 12, right? It's pretty unusual, but it does happen. It's happened here. I won't call it FOIL because it's not really FOIL, but what you do is you take the first guy and you multiply it. So what do I get? I get x squared times 6x is 6x cubed, and x squared times 12 gets me 12x squared. Then what you do is you take the second guy and you multiply them by these two. So you now get 2x times 6x, which is 12x squared, and 2x times that is plus 24x. And now it gets kind of messy, so I won't do the arrows. You lastly do 1 times these two. So you'll go 1 times 6x gets you 6x, and 1 times 12 gets you 12. Is there anything tidy? Yeah, we can do a little bit of tidying up. 6x cubed, 24x squared, 30x's plus a 12. And that is meant to fit in there, so I'm going to have to write really small. That's going to make it 6x cubed, 24x squared, add 30x, add 12. And the whole thing is still over 3x squared plus 12x squared. Can you see there's going to be a lot of algebra in these questions? Aren't you going to FOIL things and collect terms and occasionally, hopefully, factor as well? So what I'm going to do now is, do you notice I put the negative there to represent, subtract all of them? Right, so here goes. 6x cubed, take away 6x cubed. Ooh. Right, 6x cubed, take away 6x cubed. That was a nice surprise. 24x squared, take away 24x squared. Wasn't that a nice surprise? 6x squared take away 30 is negative 24x squared. 24x doesn't, oh, got that wrong. I got that wrong. I just have 6x squared. There we go. 24x take away this guy leaves me with negative 6x. And negative 12 is that. So I've still got a fair amount of cancelling. So FOIL it out, collect like terms. So it's better than it could have been, right? I need some help here. It's not much, but is there anything that you could do to make the top just a little bit nicer?
Simplify.
Okay, how are you going to do that? What
Factor
you-
out of 6.
I like your thinking. And then you have another look. I could imagine that being the final answer in lots of cases. But I had another look at that now that you told me correctly what to do with the common factor. Can you do anything more? Because I can see one more thing.
You can factor the x squared minus x plus. I can't speak today.
I know
minus
what it
2.
is. You can factor it. Do you know what the factors are?
X minus 2, x plus 1.
And at that point, can't you say, thank goodness this question's finished. I've taken it to the point where it looks like the original, and haven't we factored the heck out of it? Have you noticed that you don't do anything to the bottom squared? So don't go foiling that out. It never does you any good, right? Whatever the bottom is, just leave it alone, call it what it is. So all your work, all the hard work, isn't it going to be on the numerator, right? The denominator is just going to be whatever it says squared. But the numerator, that's the case. Now, occasionally, it hasn't happened yet, but it will happen in the question. You might get a 3x squared plus 12x up here. If that happens, you are allowed to cancel. But only because it's a factor, right? That's not happening or doesn't happen that often. Okay. This is a version of question 7. Oh, they've decided to call it G of t.
Yeah.
That's fine. I prefer y, but that's okay. Now in this question, the top's always f and the bottom's always g. We're going to find the derivative. And it's going to be f dash g, take away f of g dashed over g squared. One of the reasons I don't like these functions to be called something else is that isn't there a g here and there's a different g here, right? This g means that guy, right? This g means the whole package. That's kind of why I don't like it. Wouldn't it be much nicer if they just said y equals and y dash, right? So if you're wondering what the heck's going on, that's it. Okay, you got 2 minutes. Go for it. You finish that one. And remember style points. Okay, let's do it. If you differentiate 7, take away 3t, you just get the number -3. You leave g alone. Subtract, leave f alone, and multiply by g dashed, which is times 4. And then on the bottom, 4t plus 5 all squared. Next thing you should have done is distribute that. So -3 times that is -12t. -3 times that is -15. I could probably do this in one go. If I call that -4 times 7, you get -28. And -4 times -3 gets you plus 12t. That was interesting. And that's over 4t plus 5 squared. It looks like I get -43 over 4t plus 5 squared. Is that what you got? Because I count wrong sometimes. Okay. And would you agree that's as good as that's going to get, right? There's nothing much you need to do about that. So let's keep adding complications to the problem. This is a version of question 10.
I have a question about
Yes.
the last problem.
Mhm.
How did you get negative 43? When you distribute the negative, then it's also a negative 12t on the other side.
Oh, I'm trying to say. So I had negative 3 times these gave me those two terms. You're okay with that?
Yes.
Okay. So what I said is 4 times 7 is 28, and then make it a negative. 4 times that is negative 12t, but you make it a negative, it becomes a plus 12t. So these
Mhm.
two on the outside kill each other off. And I hope
Okay,
that
I was putting a parenthesis around the 28 and the 12, and I left the negative or the minus sign in the middle. So I think that's what
that's it. Yeah.
yeah.
If you wanted, you could put another line in here where you did this guy in the first brackets, take away this guy in the second brackets, and then you could see the subtraction of both terms, maybe a little bit clearer.
Yeah, I'll have to do that. Thank you.
Okay. So what's weird about this one? There's only the number 1 on the top. Sometimes the simplest things can throw you. So it's f dash g, take away f of g dashed over g squared. Well, right off the bat, what is the derivative of the top? 0. Yes,
0.
that's what I saw. Your lips were moving, but I could read what one of you was saying, right? Take away 1 times the untouched g, all over the g bottom term is g squared. Now, won't 0 times anything just basically disappear, right? 0 times anything is 0. So that term is gone now. And all I've got is negative 1 times all of it. And remember, it's a distributed thing. So what do I have? I have negative x to the 4, negative x squared, negative 1.
Supposed to be the derivative.
You are right. So it's going to be 4x cubed plus 2x. Well done. And so that's nothing. And here you've got negative 4x cubed, negative 2x all over this guy. Style point. You can do a little bit better. It's pretty good, but we can do better. What can you do to the top?
Factor out the 2.
Okay. Anything else?
And the x.
Right. If you're going for it, couldn't you also take the negative as well? Now, if you took out negative 2 and x as a common factor, this guy becomes plus 1, and this guy becomes 2x squared. Or you could just pull out the 2x, in which case you would get that. I think both of those are equally good, so I wouldn't have a problem with that, right? So if you just saw the 2x and left that, that's fine. If you saw the negative 2x and left that, that's also fine. So, yeah, both are good. Pick whichever one you like. I just got a little signal. I don't know if you hear it. Do you hear it when my earphones say, what was that? It says something like batteries need charged. Did you catch that? No, my earphones talk to me when my batteries are going dead. Evidently, it doesn't necessarily get through to you. But that's bad news is that I may lose my battery power and my ears. I won't be able to hear you or your questions, in which case I'm just going to keep going, but you'll have to do it by writing. So the next cell we're going to look at is 11. and it's a square root of x over a square root of x add 7. And I'm going to rewrite that as an x to the half over an x to the half add 7. And we're doing it for the same reasons we typically do this for any square root. Because I'm going to differentiate it, I need it to be written as a fractional power. So it's going to be f dash g take away f of g dashed all over g squared. If you differentiate this guy, you get 1/2 x to the negative half power. That's the power rule. Times this guy. Take away, leave the top untouched, and differentiate this guy, and you'll get 1/2 x to the negative half. And the whole thing is over x to the 1/2 plus 7 squared. So f dashed g take away f g dashed. So far, so good. Now, style points, make it look pretty. Well, I'm going to essentially distribute these two, take away, distribute this thing. And that leads us to a very interesting multiplication. When you multiply 1/2 x to the negative a half with x to the positive a half, what do you get? It might be a surprise, but what do you get?
It looks like you should,
Keep talking. It looks like you should.
it looks like you should get x to the 0, which is 1.
Okay, and 1/2 times 1 is 1/2. Kind of surprised. Would you expect all those fractions to be just ugly powers of x? But it ends up just being 1/2. So this times this is 1/2. This times this is just 7/2 of x to the negative a half. This times this is negative 1/2. And while I'm at it, why don't I turn that into a square root so it looks more like the original? And this half gets killed off by that guy. And now I'm looking at this. That is not very pretty. I'm going to rewrite it over here. The rules for style points are make it look like the original and factor the heck out of it. There's really no more factoring to be done. So I'm stuck with the make it look like the original. And unfortunately, that isn't a positive 1/2. Isn't that a negative 1/2 power? So that kind of makes things a little bit more awkward. But nonetheless, I'm still going to do it. How could I write x to the negative 1/2 so that it has a square root in it? Put in a little bubble over here. How could I write x to the negative 1/2 so it would have a square root in it?
7/2 square root x.
Oh, okay. So if we put the 7/2, you're saying that. Agreed? Now, if that was positive 1/2, that would be true, right? So how do you cope with the negative 1/2 bit? Because you're like 90% there, but you're a little bit more to do. That's a negative power, isn't it? If it was a positive, that would be the answer, but it's not. It's a negative 1/2. So what is that?
The square root x is right next to the 2.
Yeah, it's on the bottom. That's that guy. So we now have that fella. Agree? And now I'm going to bring These two downstairs. %80 of that question was pure algebra. Wasn't this the only derivative part? Wasn't everything making it in a form we could differentiate, and then a lot more work at the end where we had to get it as simple as possible and also at the same time to have square roots in it, because that's what the original had. So your skill base for being good at these questions is to be good at algebra, right? How to manipulate things, how to factor things, how to FOIL things, combine things, and all the other terms that you would use in an algebra situation. That was a good question. That is a hard.
What algebraic process did you use to bring the top denominator down to the bottom denominator?
Okay.